Drones, sensors, photogrammetry, field spectroscopy, and remote sensing. These are just a few concepts revolutionizing machine perception. Within the Institute of Cartography and Geoinformatics at ELTE's Faculty of Informatics, a research group demonstrates every day how modern digital technologies can be harnessed for research, science, and industry.
These are not armchair scientist topics. We are forced to go out into the field. Our strength lies in equipping our platforms that allow us to create added value from the diversity of the collected data. During image analyses, we measure these data sets, a process we refer to as data fusion or image fusion. And from the results of these image classifications, we can determine the nature of a given problem, how it unfolded, and its temporal and spatial characteristics.
An RGB camera records 3 basic colors for each pixel, just like our smartphone camera, measuring values on 3 spectral channels, or bands, within the visible range: red, green, and blue. The RGB sensor is a so-called passive remote sensing device, meaning it detects the sun's reflected radiation. Multispectral sensors can capture images simultaneously across 4 to 10 wavelengths. This allows even the near-infrared range to be visualized through what is called color shifting, associating invisible spectral ranges with visible colors. Multispectral cameras are particularly useful in precision agriculture or, for example, in crop condition monitoring. By contrast, a hyperspectral camera can record a complete spectrum for each pixel, capturing hundreds of bands. The adoption of hyperspectral technology is expected to spread widely and play a significant role in numerous research and industrial applications in the future. The group's research topics are diverse, ranging from scientific publications to industry-ready systems.
We have a permanent core team of 5 to 6 people who are primarily involved in carrying out field measurements, contributing to a wide range of thematic research tasks, and working in close cooperation with various external partner institutions. It is especially important for us when our work results in something tangible, either a product or a solution that has clear industrial relevance and real application potential, or, from a scientific point of view, when our research leads to high-quality publication and a meaningful scientific contribution.
The ELTE labs are well equipped, giving students access to state-of-the-art instruments for scientific research purposes.
In this sense, it's very important for training the next generation that young researchers and beginner PhD students are able to see real, authentic field research and to take part in it themselves.
Heading out to the field, the archaeologists of the Lotskor Dejeu Museum in Veszprém guide the research group to a previous excavation site. On the now abandoned military firing range near Gyulafiratot, excavations are underway of a Roman-era villa estate. Beneath the surface lie the ruins of former residential and agricultural buildings. Excavations were already carried out here in the 1930s. But what additional insights can modern technologies provide for archaeological research?
My big question is still whether we can really align the site plan from the 1930s with today's findings. At this site, our goal is to refine existing knowledge to see whether this method or this device can truly add something new.
We are conducting surveys using 2 types of sensors, a simple RGB camera and a laser scanner. We are examining how much higher resolution data the LiDAR sensor can produce compared to the RGB camera data, and how accurately the derived terrain model can localize the remains of this villa estate.
LiDAR, or light detection and ranging, is an active remote sensing technology. During operation, it emits laser pulses that are reflected back from the examined surface or object. This technology enables highly accurate distance measurements, producing a 3D point cloud. From this, detailed maps and models of surfaces or objects can be created. LiDAR's advantages are high precision and its ability to quickly survey large areas in great detail. Survey conducted with the LiDAR and RGB sensors is a non-destructive technology, unlike archaeological excavation, during which artifacts can be damaged. After assembling the drone used for the survey, the team records the coordinates with a high-precision geodetic GPS.
After assembling the drone, we set up the high-precision, or RTK, real-time kinematic GPS base station. This is crucial because the drone survey allows only for meter-level spatial accuracy, while geodetic GPS improves it to a few centimeters, or ideally even sub-centimeter accuracy.
The drone records the data while flying along a pre-planned route. This process only takes a few minutes.
Meanwhile, the drone has returned. What we just recorded are the laser reflection points from the surface. From this, we will construct a continuous surface, a plane, a 3D model, and essentially a digital terrain model.
This is ELTE's laboratory, where researchers analyze the collected data. After downloading the recordings made with the LiDAR and RGB sensors, a photogrammetry or geoinformatics software is used to produce a 3D terrain model and an orthomosaic. The so-called orthophotos are scaled aerial images free from perspective distortion. By stitching together several orthophotos, an orthomosaic is created, which covers a larger area and provides a uniform visual representation, useful, for instance, for mapping or geoinformatics purposes. The terrain model generated from the images with height coordinates can already provide new insights into the archaeological site.
Traces become visible that simply cannot be detected with the naked eye during fieldwork. Here we can clearly observe the slightly blurred buried ground plan of the larger western building of the villa estate, which has remained hidden beneath the surface. In addition, we can identify a smaller agricultural building that was completely cut through by a trench, as well as another structural remnant located further to the east, indicating the broader extent of the site.
Geological mapping has been carried out in Hungary for several centuries. With the help of modern technology, large-scale geological and topographical maps are now produced using drone imagery, LiDAR surveys, and geodetic GPS data. These highly detailed datasets enable spatial analysis and 3D modeling and serve as the basis for stereophotogrammetry.
I'm both a cartographer and a geologist, acting as a link between geoinformatics, drone imaging, and geological research.
From RGB drone imagery of Sirok Castle Hill, Gaspar Albert is now building a 3D model. This allows the rock to be examined from multiple angles, for example, to determine the directions in which its fractures developed and whether they reduce the rock's stability. This method also helps predict future geological hazards, such as landslides or slope movements.
Here you can see a so-called marker bed that has been mapped and drawn in. This layer is also clearly recognizable directly in the terrain. And if I zoom in closer, it becomes visible that the narrow neck of this small rock formation has been eroded over time. This is a pumice-rich layer formed during volcanic activity, containing a high proportion of easily crumbling particles deposited from volcanic tuff. Because of this composition, the material has been especially susceptible to erosion, which has gradually worn it away over long geological periods. The 3D polyline segments shown here with nodes marked by numbered 3D coordinates can be used to mathematically fit an approximate plane to the surface. This allows us to determine how much the layer has tilted or shifted since the time of its original formation.
ki a réteg.
In another project, we developed an innovative life safety system for potential chemical plant accidents or disasters. It speeds up rescues and can help prevent the spread of industrial fires.
We want to support and complement the work of industrial firefighters. A drone equipped with an RGB camera is dispatched to the site where an alert reports an unexpected event or disaster.
The main goal of this project is for the drone to provide rescue units with continuous, real-time visual data on the possible spread and direction of the fire, as well as information on whether people are present at the disaster site. This system is also equipped with a thermal sensor, or heat camera, which provides additional detailed information about temperature conditions.
The thermal camera can be used not only for locating people, but also for monitoring the condition of various tanks. On the screen, we can clearly see, for example, how much liquid is contained in these tanks, and in the corner of the image, the gas levels in the gas cylinders are also visible.
The spread of imaging sensors has revolutionized modern research, revealing a world once invisible or barely visible, one we could only imagine before. Machine perception has opened a new era in numerous scientific fields, allowing us, for the first time, to truly see the world from any perspective. This not only yields new knowledge, but also fosters a fundamentally new kind of scientific thinking.